It's not even open on my computer. Can you see the evaluating linear regression models, Michael?
No.
Now?
This
No?
just says graphing with ggplot 2 package.
Okay. All right. We're going to stop. So at work, we don't even try to use Teams anymore because it never works right. So, all right.
See it?
All right, we're good to go now. I believe we're recording. Yes. So regarding the videos for the class, I've gotten most of my videos edited, and they're gonna be up soon. Today, since it's been a long time since we've had a class, I'm gonna be doing a lot of review of linear regression in general, and also because it's just the hardest concept we've looked at so far. So I think a little bit of review is warranted regardless. So I'm gonna get started with that. For where to find the link to, if you want to join live so you can see the screen on your screen, you'll go to my website, which is www.kelseyhunsberry.com. Click on data science classes or put it in with the link, and then all of my materials are on my website. So most of the classes, the last couple have not been put on yet, but I'm working on it. Just been crazy with the holidays.
Okay, so this program, are you doing this in conjunction with this Austin Library?
Yes.
Sponsor, things like that?
Yes, the question was, am I doing this class in conjunction with the Austin Library? It's an official program here at the library. So I do both programming, R programming, and statistics. So one thing that before we start, so after this, we're going to be getting into the AI stuff. I'm going to continue remotely and as well as in person doing this class. So we're going to be getting into machine learning. So I'm in a little bit of a pickle regarding what I think I should do with that. So R is terrible for machine learning. If any of you know about this, it's better for classical statistics, but it tends to, say, cache everything to memory. So it pulls it onto your RAM, and then it moves pretty slowly. So if you have a big data set with machine learning, it just won't run on R unless you go on to, say, AWS and have a bigger amount of RAM. So I have been learning, when I learned, I did a little bit in R, but I also learned in Python primarily how to do it. But I am not a Python expert. I'm sort of like, I'm functional, but I can write R like I write English. It's really easy for me. And that's what I've taught throughout. So my question to everyone, I'm planning on going on and teaching the machine learning with R, just because in general, it tends to be, the hardest part is the concepts, not really the programming part. But I kind of wanted to get some feedback on whether you guys would prefer to move into Python, even though I haven't taught it and I'm not an expert in it. I know how to use it, or if we should keep going in R once we get to that side of things. Any feedback in the room?
Another script language, is it?
R just caches everything to memory, so that's the problem. So if, say you're using I recently used to train a model with like 1.5 million rows. I tried to run it in R, it failed in 30 seconds due to an out of memory error. And then I moved into Python and it ran in like 5 minutes successfully. So that's the problem. If we're using a small data set, I can definitely use R. And honestly, it's more the math. Like, learning to code it is the least of the problems of doing it. I mean, it's just hard, the math part. Whereas the coding part is usually just a couple lines, other than data manipulation. So, you guys have any feedback?
I think we should do Python.
So put it on, you actually can use R on AWS. We do it at work, but it's a lot easier to use Python. So somebody asked about, like, can we learn it in Python so we can use it on AWS? So, and Michael, what did you have to say?
Go for Python.
You prefer Python. Is there anyone who really, really prefers R? Because we would be switching. Okay, anybody on the line? I'm gonna open the chat just so. So I'll go forward with that, I guess. So in one of my next classes I'm going to do, I'm going to show that project. It's a personal project I've been working on from beginning to end. I'm going to show how it works and just go from the data munging up through the actual visualization at the end. And I'm going to show you what a full life of a data science project looks like. So that's one that is coming up, which I think could be really helpful for you guys to get an idea of what it looks like for if you were a data scientist in a job. So, all right. Well, I will get started. I'll plan on doing Python then, and we can go forward from there. All right. So I'm going to do a review real quick because I think we got a lot of new people in the room on simple linear regression, and I think we just should do that anyway. So linear regression is a model that predicts the relationship between the response variable, which is a continuous variable in this case, and one or more variables that are called predictors. So you model that, you use this model to then use those response variables to predict, use the predictor variables to predict the response variables. And there are there's information that comes out of that can look at what type of relationship that predictor has to the response and what the magnitude of it is. So correlation, which I'll have the videos up soon, is more, you can only look at the relationship between two variables, two continuous variables. So anything that you do, it's not going to just be a relationship between two variables. It's going to be a relationship between many variables. So this is the easiest model that puts out predictions that are actually useful. So I'm going over this, and then we're actually going to move into the AI space. But it's really important. I've read over and over that logistic regression, which we'll cover in next class, and linear regression are the most used models for data scientists, which is a little surprising to me, but apparently it's true. Because it is the simplest. So if you make a model and you get the same results from a linear regression as you do from a more complex method, you'd want to use this. Just by a rule of thumb, the simpler, the better, if it's effective. But as we'll see here, there are so many assumptions that you have to assume in order to use it properly, which is the downside of it.
I have a question.
Mm-hmm.
So I get really confused remembering all these terms like linear, logistic, multiple. How does linear regression differ from multiple regression?
So simple linear regression, and I think I get into this a little more, but simple linear regression is just one predictor variable and one continuous variable. So it's very similar to correlation. It's not the same, but it's very close. So we're looking at that one variable and then our continuous variable response. Multiple linear regression is two or more predictors predicting the response variable. And we're going to go over that. Haven't gone over that yet. So I'm going over the simple just because it's a lot easier to conceptualize before you move on to using more variables. Logistic regression is when we're predicting a categorical variable. So say you're predicting that accuracy, like if a drug works or not. So yes or no, the drug gets rid of whatever pathogen it is, and then you would have predictor variables that predict that yes or no variable. And then today we're going to go over several examples of the linear regression side of it. But so logistic is categorical, linear is continuous when we're talking about prediction. So go ahead.
So when you said predictor variable, is that the one that's already known, and response variable is the one that you're trying to find out?
Yeah, so we're looking at the relationship between those predictors and the response variable. And I'm going to get into it a little bit more. So here, this will start to come together. So linear regression, it basically is going to predict, it's a linear model, so it's going to predict the line based on different predictors. So the simplest is when you just have your response variable and you have one predictor variable, which we're going to cover that to start here. So one of the best ways to see it is a scatter plot, like you see here. So we can conceptualize this as the predictor variable, and this is the response variable. And then all of these dotted dots would be where the points fall in this space. So, and I will give, I think it will be easier to go into my code to see an actual example of this. So opening that up. So my code is, if you go to that data science class, all the way to the bottom, my code will be there. So it's kelseyhuntsberry.com. It's on the OneDrive. So I am going to show. I also apologize, now that I've been using Python so heavily, I always click enter and like shift enter, which then deletes your whole code instead of command enter. I keep getting confused between the two, just because I've been more used to that now. Okay. So this is going to be a little bit easier to understand like what we're predicting. So one of the examples we're going to be using in this class is we're going to be predicting heart disease mortality, and in one case, life expectancy, with a lot of different variables directly from the census. So I got, and this is an example of one of the census variables. We've got percent below the poverty line, and which is around, I think, $14,000 is the poverty line. It changes every year by a little bit, but it's ballpark around there. And we will be predicting the average heart disease mortality in 2014. So this is going to be our example to start out.
So in here, which one is the predictor variable?
Yeah. So the question was, which one is the predictor variable? You choose that. So in this case, we want to learn about the heart disease mortality in this case. So that's going to be our predictor variable. That's what the question you have to ask yourself is, what do you want to predict? Because this is similar to a machine learning model, just to expound on that a little bit. So the goal of a machine learning model is to take predictor variables and then predict some response variable. So what we call and what we see here would be our training data. So we use that to train the model to explain that response variable. And then the idea is eventually, if you get a model that works well enough, we take new data that's totally different, we plug it into that model, and it will dump out our predicted heart disease mortality rates. And so we can have an idea with totally new data where we haven't seen the heart disease response variable yet, and predict that in like future times. Let me give an example. So one of my models that I was very successful, it was not linear regression. We did try it. It was something similar. So I was working on a seed production model. So basically you have to produce enough seed in order to test the products. I worked at an agriculture company. So we needed at a testing pipeline that was so many years long, and there was a minimum value of the amount of seed that we could have. So in order to predict that, because if something wasn't, one of our products wasn't going to do well, and it was going to have a really low seed return, we wanted to know that ahead of time. So then we could add more resources to that particular product. Same at like if one of our products was predicted to do really well, we wanted to then know that so we can allocate the resources from that product to somewhere else that needs it more. Because as in most companies, there's a finite amount of money and time that you can put into something. So you want to, and that's usually the idea, is predicting something before it happens. And giving information so you can maybe reallocate resources or prepare for something that's going to happen. Another example is like if you work in retail, a sales forecast. So we would be predicting sales before they would happen. But in this case, so I took a lot of different predictor variables. I tried a lot of different ones. I did a process similar to what I'm going to show today, found the best model, and was able to, a pretty high level of accuracy, predict how much seed would be produced for each one of these products. I can't give a lot more detail than that just because of confidentiality reasons. But so we had this model, and then that was the training data. So the thing that we built the model with was 3 years of data. So say, for instance, 2015 to 2017 we had. And every year we wanted to predict the next year's data. So, and say in this example, I wanted to predict 2018 before it happened. That next year or this year, it would be predicting 2020. So I would then take that model that I predicted, use and validate. Like, so it looks, it was to a level of accuracy that we were comfortable with. And then I put that, say, 2020 data, I plugged it into the model. Then it would spit out the predicted seed return. So that's what you would eventually want to use this for. And that's why, and a lot of people want to eventually in this class learn about machine learning. This is the most simple model that you could use for that. ANOVA, you technically could, but it wouldn't, it's just the sample mean that we would use as the prediction. So here it actually, if you're predicting a continuous variable, it's going to spit out a continuous variable. So in this case, it's something similar to seed return. So how much seed would be produced in when we're trying to produce that seed, like, and that's going to be based on weather. It's going to be based on location, things about the different products, like attributes of that particular product. So that's the end goal here. And there's a lot more to it than that. Like, one of my classes is going to be on how to validate a model. And I can't go into that in detail because there's a lot of really, there's a specific way to do it. But that's for another class, but we got to learn this first, kind of.
So quickly, what's the response variable?
So response variable is what we're trying to predict. So in this case, it's we want to know or predict the average heart disease mortality. I'm going to open real quick. So we have this is the data that we're using in this case. So, and there's going to be a lot more detail on this as we go through. But this, I decided that I wanted to know more about heart disease mortality. So you have to have some idea of the domain or the area that you're looking in. So it's basically the variable of interest that you want to learn about. There's predictor variables or things that you try to see if they accurately predict that heart disease mortality in this case. So we're going to use census data for that. So demographics in this case. So the demographics, and you'll see each row is a county. So this is county level data. And so there's a little over 3,000 observations in here. I think it's like 3,100 something. So that's the data we're using for the beginning of class today. Well, we're using this data, but we're focusing on heart disease mortality to start. Okay, so back over to the graph for a second. So this is a scatter plot, and this is usually how people, since this is simple linear regression, we're looking at 2 variables, the response and 1 predictor. So in this case, we're using the percent below the poverty rate. This is 2014 data. I am going to real quick close the door.
So the percentage of poverty,
Yes.
that one is the predictor variable.
Yes, in this case, and that's something I want to try. You don't know anything about the predictor variables until you model them. And then the model will give you information. And that's kind of what we're going over today, is how to get that information about the relationship between 2 variables.
And the bottom is the response variable.
Yes, the percent below poverty is the predictor, and the average heart disease mortality is the response. That was the question. So in this case, theoretically, the model will spit out a straight line that goes through this graph and tells us the predicted value of the average heart disease mortality rate using that poverty rate. I can't remember if I did put it on here. Looks like I didn't. So you can also put a linear model actually on your graph, but I don't think I did do that. So we'll go back to this example. So we're seeing here, so imagine this as the average heart disease mortality, and imagine this as the percent below the poverty rate. So these red dots would be our training data. So the points that we're using and we're putting in the model. What the linear regression model is going to do is spit out something that looks like this blue line, which is our predictions. So say we have, and I'm going to zoom in a little. So say we've trained our data, it looks good, we have our model. And we find that one county has a percent below poverty line of 15%. The way that this would work, it's mathematical, and I'll go over more of that later, but we would say it just visually would come over to see where that 15 met the line, and that would be our prediction down here. And you're probably wondering, well, that's not very accurate. Like, how are we actually going to get some useful information from that? This is only two variables. You can use more than that. Nothing is a relationship between two things. There's always more factors. But this is the most simple example so we can understand it and go on to the next part. So that straight line gives us a prediction. You'll see that there are lines between the red dots and the line, the prediction line. That's error. So our error between those, that training data and what we actually predict. So what we're seeing here, this is our actual value and this is our predicted value, and it's going to spit out the error. So that, and we're going to be talking a lot about error going forward. So this is important. Notice I'm starting to use the notation just because you have to get used to that. If you go on to machine learning and don't know any notation, your brain is going to explode. So we have to start learning that. Anything with a hat over it, all my statistician teachers have always called it Y hat. So Y hat is always the predicted. Y is our training data. So, and if we look at the I, it's going to mean our first data point, second data point, third data point, all up to, in this case, like around 3,100. And same thing over here. So this will be our actuals minus predicted is our error. And the goal of linear regression is to minimize our error. So we minimize the amount of distance, so the black lines between the red and the blue line. So does that make sense?
How's the blue line being determined?
That's coming.
Okay.
Yep. The question was asked, how is the blue line determined? That's coming in just a little. Go ahead.
So you said minimizing the squared errors. So are you trying to minimize yi minus y hat squared?
Yes, and we're going to get more to that. Like the actual formula is coming very soon.
So why are you trying to? Sorry.
Mm-hmm.
So why are you trying to minimize the squared errors and not the errors themselves?
You're getting too far ahead. We're not talking about the squared errors yet. So, I should have put minimize the error. Okay, let me get to this real quick. I think we do need to skip ahead for that. Okay, I've probably written this a little sooner. So squared error, I am going to go into that. Okay, so why do we minimize the squared error? So you're seeing some of our predictions here, so our red are above the predicted line. Some of our predictions are below. So say we added all of the values together and then evaluated our model that way. Well, say you had a model that had values way up here and values way down here, it would actually look good, even just if the positive outweighed that, if they were similar, the positive and negative values, no matter how far away they were from the line, it would look like a good model, which is not the case. So when we do this, we're looking at the squared error. Why we do that is when we square it, we then get rid of that positive or negative sign on our values. So it makes everything positive. The second reason is when we're squaring it. So if we have that like whole numbers, it's going to make our error values bigger. So if you have values of 2 and 4, you're going to find a difference of 2, and then when you square it, it's going to be 4. So that also penalizes or like makes it worse when our predicted values are way far away from our line. So it will be, the model will be penalized or for the stuff that's really way far out, because that's really what we don't want. We don't want to miss by a ton. So that's why we're looking at the squared error in particular in this case. So, and then there's more to it. We're actually going to find the mean squared error is root mean squared error is usually what's in a lot of machine learning models. It's used as well. So because we're finding that squared value, we're also going to find the square root to kind of make it similar to what your actual values would be. But then it's more of an average. But we'll get more to that in a second. That's more of a, so.
You had your response variable on the x-axis.
Yes. Yeah, so I probably should have done it the other way. I never actually modeled it with the line. So in general, the y does go here, and then the x goes down here. So that was a mistake on my end. But I didn't actually use that until later, and I don't think I actually plotted the model. So unfortunately, I should have. Yeah. Are there any other questions? Go ahead.
Okay, so to talk about that, does it really matter though if x and y are shifted?
For graphing purposes, no. For actual modeling purposes, yes. So, which is why it wasn't such a big deal. So, and that's actually the next slide. So when a linear model, and this is simple linear regression, remember, and we'll get towards the other stuff in a little bit. In simple linear regression, the format of the prediction model is always going to look like is shown here. So this is our prediction model. So this is why it matters what order. So our y is always going to be our response variable, what we've been talking about here. BO is always our y-intercept. So going back here, the y-intercept in this case would be like around 6 because it's crossing the y-axis at 6. So it basically positions the initial part of our line you can think of. So that's always the first value. Then they're summed or subtracted based on if the next value is positive or negative. This is called our coefficient, so B1, and the next slides are all about the coefficients. But this, you can think of it as a weight variable. So, and X will be our training data or what we eventually want to predict later on. So in this case, for our purposes, it's all of our training data or all the observations that we're using to build our model. So we would go through 1, 2, 3, 4, 5, 6, and then would have this in the X value. So you basically, if you wanted to know for one county, the Y value or the response variable, you would take that percent below poverty line, plug it into X, it would multiply by the coefficient, and then you would add the Y-intercept, and then it would give us our predicted average heart disease mortality. So we'll get more into the actual coefficients because that's a really important part. So I'll get into that. I'll ask for questions in a minute if there's still some. So when we are estimating coefficients, I am putting formulas. When you're beginning, it's probably more important that you get the broad idea of what it means. You never do this by hand, but I am putting the formulas in here because the more advanced you get, you really are going to want to understand how these are actually calculated. But when you're beginning, try to get the big picture versus maybe the details. And then the next time you can maybe read something after you leave here, and then you can get more into the nitty gritty of it. But so at least for now, unless you have statistics experience, try to understand the big picture. So in this case, when we estimate our coefficients, you'll remember from past classes, this means sum. It always means that particular symbol, it always means sum of. So we basically, and this I is telling us that we're going to go from I equals 1 up to the n value in our data, so our sample size. So if we have 3,100 data points, we're going to plug into each of these, each point from 1, 2, 3, 4, so on and so forth, up to say 3,100. And then we're going to do the sum, make the sum of this for for each individual point. So first, we're going to do our first value. We're going to plug it in here. And the bar always means our sample mean. So bar, in this case, it's going to be the sample mean of everything. We're going to take that first value minus the sample mean, all of our observations, so for our x values. Then we're going to do the same thing for that y value, our response variable. And this is training our model. And then we're going to subtract that mean value. And then we're going to divide that by the squared error. So we're going to take that sum and then basically take that error value and square it like we just saw before. And this gives you our weight. So you can think of the weight as almost an importance value. So how important is that predictor variable and how much weight should we give it? You can think of it kind of that way. And then to find the y-intercept, you basically take the output of this and plug it in here. So our coefficient, and we have our sample mean, so x there, that's our predictor, and we have our response variable here. So y minus the coefficient times the sample mean. So now to get into a little bit more, I'll stop when I'm done with the coefficients and we can go back if we have questions. So a positive coefficient, because you can see here, if we're getting a negative value here, that is going to mean that our relationship is positive. So that means that a predictor, it rises as a response variable also rises. So that's what we think of as a positive relationship. And I thought I showed this when I went over correlation visually. But so if it was a positive relationship, what we're looking at. So I'm going to choose actually a different metric. So because a negative, we're going to see a negative relationship with our particular problem. So if we wanted to look at heart disease mortality, something that would likely have a positive relationship with that would be, so something that goes up as heart disease, so as the percent of the poverty goes up, our heart disease mortality is going to go up. So that is a positive relationship. The other thing is a negative relationship. So one of our values is going up, and the response variable is going down. So the predictor is going up, the response variable is going down, for instance. So something that would look like that. Trying to think of something in this particular example that would, we'll see something down the line. But when our response variable is going down, our predictor variable would be going up. So that's our coefficient, and that's how we can think of the weights. So if we looked, say we had a 2 of a coefficient, so that would tell us that our weight is 2, and then that our values are increasing. Both are increasing. So I'm going to get down real quick. I guess I didn't. Yeah. All right.
I have a question. That formula?
Yeah.
Formula, is it out of the book formula, like in the standard formula?
Yes. Yes. So that's what you'll use in every case. All right. So we can then, I'm actually going to stop here. So I'll go over the p-values, which is the significance, in a minute. Are there any other questions about this? Fire away. Because I'm learning how to explain this stuff as well, so I want to stop.
So when you say coefficient in the formula, is that B1?
B1. Correct. So weight coefficient, it's going to mean the same thing. So if you have a percent below poverty line of 30%, in order to get our response variable, and say our coefficient, for instance, is 2. So it would take that 2 times the 30, and then it would add whatever our y-intercept is, and then we would get our response variable. We're going to see more about that in a little bit, but that's the basic concept. Okay. Yeah. Feel free to put questions in the chat if you need.
Okay, you go to the next slide, please.
Next slide. Yes.
So here you're calculating the coefficient, but how do you calculate the, what's the other one, y bar?
Y bar. So how do you calculate Y bar? So that's just the grand mean of all of our observations. So of all of our predictors. So we just find the mean value of, in this case, it's going to be the percent below poverty line. So we find the mean of everything. The Y bar is going to be the mean of our response variable, which would be the mean of the average heart disease mortality rate. So that's our response variable. So all of our observations added up, divided by the sample size. It's all that is. Yep.
So the y bar and the first formula and the second formula, you can put them in the same thing. It's just a mean.
So the question was X bar and Y bar, they mean the same thing. It's just a different variable we're looking at. So Y is always our response variable, so, and bar will always be sample mean. It's always, you're always going to see Y bar. You'll see that every time, sample mean. So Y would be the average of the Y response variable, heart disease mortality. And X bar would be our predictor variable, which is the percent below the poverty line. So, and that would be the mean of all that. So we're basically, here's a good way to explain it. So backing up a little bit, you can think of the mean as a baseline. So if we didn't have a model, we would probably find the mean value and use that as our predicted variable, because that's the best way to do that case. We're trying to improve upon that, is what you can think of it as. So our null, or you can think of it similar to a null hypothesis, or our baseline value, we're going to use the mean. So if our model improves upon the mean, then it's going to be a better model. So that's why we're using this mean value, and we're subtracting it. So we want to see how much better our model is, and we want to improve upon that mean value. So you can think of it sort of like that. And hopefully that helps a little. And that's what we're doing down here too. But remember, we want to keep the bottom positive, because say this comes out as negative. So our mean is bigger than our response variable in this case. That's going to output a negative value. But we want to divide by something that's positive so that we can then see that it's a negative relationship. So that's where we're seeing the squared come in, is down here. So we'll always have a positive value up here. If the response variable is going to be, predictor variable is going to be bigger than the actual mean value, it's going to then output something negative. And then we can see that one of our variables is going up when the other one is going down. Go ahead.
Is this a similar measure to like correlation?
So yeah, so that we went over in the last class, the question was, is this similar to correlation? Yet, so we went over that in the last class. I'll have my videos up very soon. The biggest difference, the formula looks very similar, actually. The biggest difference is correlation goes from 0 to 1, and coefficients can go from, they can be anything. So they can go as big or as far as you want. The denominator is different. So the top, it looks the same for correlation versus coefficients. But we don't want to put end bounds on these. So that's why, because we're looking at more than one variable. Any more questions? Okay, just see if we have anything in the chat. Can you repeat the questions for the people far away? I've been doing that, so. All right. Yeah, are there any other questions? All right, so I'll go on, and we can, if anything comes up, please just feel free to ask it. So what the coefficients mean. So the coefficients help us get our predicted value. We've talked about that. So one thing that's very important, and we've come back to this every time we've looked at something, is it statistically significant? So say our coefficient is very small and there's not a very big relationship between the two things we're looking at. It's basically not useful to us. It will then output that value of a very high p-value. And then when we see a high p-value, so basically anything that is above 0.05 is going to be considered not significant. So basically what that would mean is we can't trust it. So there's not a strong enough relationship here to actually make our predictions valid predictions. And if you need a review on that, that is online on my website, the p-value. Also, the t statistic is also on. We talked about t-tests. You would want to go back and look at that. But the t statistic in this case is our coefficient over the standard error. So you can think of if our coefficient is bigger than our error, or a lot bigger than our error, then it's going to be a more valid or useful model. So we want our coefficient to be more important than the error of the coefficients. You can think of it that way. If you need more of a review on standard error, we did cover that as well. Our degrees of freedom, for every model, it's different. Yeah, and then in this case, you just have to know the formula. So it's our number of observations -2 in this case. So the degrees of freedom, we use the sample size and the t statistic in order to find our p-value or whether it's significant or not. R will spit that out automatically, and otherwise you have to find it usually from a table. So if it's high enough and we have a sample size that's sufficient, it's going to give us a p-value of something that comes out. So I am going to now, so this is less theoretical, I'm going to go in and start showing the code. All right. Linear model data. Okay, so I've run down, and we'll go back to the outliers in a minute, to here. So now this is what R will look like. And we're going to go over each one of these like one by one because a lot of these are important. So our formula here, you can see it looks like the y equals mx plus, you'll often see I use b1 plus bo times x. Sometimes you'll see y equals mx plus b. You'll remember that from algebra in high school. So that's what this is. You can bring that around to that. Yep, so it's a straight line. It's, this case, because we're looking at two variables, it's going to be just like a scatter plot. So we have our heart disease mortality, and then this tilde means similar to an equal sign. And we're looking at the percent of, in this case, high school graduation higher than 2014. So if we come down here, we see the 225. That's our y-intercept. So basically where the line is crossing that y-intercept, or our kind of a baseline value, you can think of it, because that's what we're going to add. And then we're going to use the weight of 1.51. So that's our coefficient in this case. So if we wanted to, using a percent of high school graduation higher than 2014, say it's 15, that would be unrealistic. Say it's 80%. We would then take 80% times this 1.5, add on 225, and that would be our prediction for that particular county. So that's what's coming out of our model. The standard error we're looking at is basically, this would be the error for the y-intercept. So how much is it going to vary? If you see really high standard errors, that's bad. So that is calculated both with our coefficient, and it also takes into account, again, that our number of observations. And our t-value is what it outputs to give us our significance. This p-value is based on whatever the t-value is. The higher, the better in this case. So these are just cutoffs. The math behind calculating the actual significance of the t-value, not a lot of people are going to know that. So this is our value. And you can think of this. Okay, I'm actually going to go real quick. So one of the things in R that's really annoying is the scientific notation. So if you didn't know how to do this, I've never memorized this, but get rid of cyan. R. So I think it would be easier to go in. This is Stack Overflow, by the way. This is your best bet for using learning how to code things. So see, this is a great example. So I don't remember what this piece of code is. I don't know how to get rid of scientific notation. Put in get rid of scientific notation in R. Stack Overflow usually, so people will get on and they'll ask questions, and some people who have a lot of time on their hands will go in and answer those questions. So that is what that is used for, and that's something that I use for the vast majority of my coding help comes from there. So I'm going to put this in and run it. Scientific notation is not within the scope of this class. So now you'll see what they actually look like. So that's what that E meant. But this is going to be a lot more intuitive for you guys to understand. Got rid of the scientific notation. So our p-value is below this value. Since 0.05 is our significance cutoff, we could be really confident that there's a significant relationship here. So if you see something that low, there's definitely a relationship. In this case, it's very, very, very significant. So that's what we're looking here. We're going to get to this stuff in a minute. All right. So are there any questions before I move on? All right. So as I said in the beginning, there's all these assumptions. And I'm going to try to go over these a little more quickly. I can put more detail online. But basically, you have to meet all these assumptions for your linear regression to be valid or worth its to give you value in good predictions. So if it doesn't meet these assumptions, you either have to adjust your data to meet them, or maybe change a little bit of your modeling, or not run it at all, depending on which one. So the first one's easy to solve. You can't have substantial outliers. So if there's an outlier way, way far in the distance, it's going to really bias your model or make it so that the values you're seeing aren't valid or they are biased by that outlier. So in this case, Cook's distance is you run your model and then you run and calculate Cook's distance, and this 1758, this value here, Cook's distance, is very influential. You can think of this as the influence on the model. This one's a big outlier. If it calls it out, it means it's an outlier if it has the number. So these numbers are our indexes. So that's a coding concept that I can show, and I'll show this in my code real quick. So in this case, we ran our model. The 17, oh, that's the wrong one. Yep. So we have our Cook's distance here. We ran our initial model here. So what it means by an index? So we're using the linear model data. I'm looking at 68, or let's look at 1757. Okay, so my values are sorted. And this is the hard way to find it. There's a much easier way. I'm just showing you intuitively so you understand what this means. You can find it with coding. 1757. That is Story County, Nevada. That's an outlier in our values. And it looks like here it's a low outlier for heart disease mortality in this case. It looks a lot lower than everything that's surrounding it. So it's too far out and it's influencing our model or biasing our model. So in that case, we actually have to remove Story County, Nevada. I did not remove these two because they're low enough and they're closer to the other data points that I need just a judgment call and decided not to remove them in this particular case. But that's kind of just, you have to decide on what that cutoff is for you. So now we're going to get rid of Story County, Nevada. So our model is going to look a lot less biased now. So now we're going to rerun that. So this is without the outlier. Now we're going to see that our coefficients are a little different, not much. So it wasn't hugely influential, but enough that our predictions would be less accurate. So that's assumption one. The next is normally distributed errors. This is the one that will make that the reason why we don't use linear regression for many things. Very few problems that you're ever going to face are going to have normally distributed errors. It just doesn't happen very often. So especially when you get into more and more variables. So we're using more predictor variables. This gets worse and worse the more that you put it on. So in order to look at that, we look at a QQ plot. So this is our residuals. Residuals are basically error. So we standardize them so that if we're looking at heart disease mortality versus a percentage, that it will follow the same structure. And down here is similar to a T statistic. But if you want more information on that, you'll have to go into my website. This is there. You can look at the t-test part and ANOVA. So if it's following close to these bounds here, these straight, or it looks mostly like a straight line, in this case it's good enough, then that means it's normally distributed. If you see something that looks like this, you've got a problem. Any pattern is bad in this case. So and in that case, you have to either transform or find the square root or the square your value and see if this gets better. If it doesn't, well, your model is not a valid model. So that's the hardest one to meet. And I found in my time, transforming your data doesn't usually help. So that's one thing why we don't. I've had people say, just use linear regression for everything. This is why you can't do that. So that's also homoskedasticity. That means that our variances are equal. That sounds like a really crazy word, but it really means something very easy to understand. So we're seeing something that has equal variances. If this side was really like the height was really small, and if you saw something over here with a really large height, basically it looked kind of like this, then you don't have equal variances. So you don't want to, I would think of, say, things that they don't use anymore, or a bullhorn, for instance. So we have to make somebody louder at an event. So the one side is going to be have a larger height, the other side is going to have a smaller. If you see something like that, that means that it doesn't have equal variances. So it also has to be linear data again. So if you're predicting with a linear line, if your data doesn't follow a linear shape, then your values are not going to be, it's not going to predict them well. That's the other problem with linear regression. Few things in life are linear.
You mentioned bullhorn. Is that a visual plot that you showed an example like that? It'll have more residuals on one side.
So this would be smaller, so a larger height, smaller height, and this would be larger, so something bigger.
Like data where the scatter was bigger on one side.
Yeah, that will have to go back to the other slides. I believe I did it in ANOVA or t-test. So if you go through my website, it'll say when I talk about assumptions, it'll have it on the titles. But I'm not going to get real deep into this just because I want to get a little farther as well. So are there any questions? I'm going to move on to evaluating our model next. Okay, so how do we know if our model is a good model? All those other numbers, that's what they tell us. So again, this is what I was looking for before, minimizing squared errors. So we want to minimize the root mean squared error. When we're looking at as our model as a whole, this is what we want to minimize. So we use that squared, so our predicted hat versus actuals over our n value. You'll see that it's squared, so we'll make it positive. And then we find the square root. So one thing that a lot of machine learning and this model has, and that are similar, they use distance to evaluate models. So you'll notice that it, like, again, go back to probably geometry. This looks very similar to Euclidean distance, or what we would think of as the miles from here and the place that my home that I came from. So, but on this case, it's on a scatter plot, the distance value. So what this intuitively gives you is the distance between our predicted values and our actual values. So that's our root mean squared error, and we're finding that squared because then it gives us something that looks like distance there. And it's finding, and I'll show here, it's similar to the distance between the actual and the predicted values, and we divide by n so it looks more like an average. So for a typical point in our data, or you can, on average, you can think of it as how big is our distance between our actuals and our predicted. That's what this means here intuitively. So that is used for linear regression, and that's the default for all machine learning models. If you have continuous variables, you can change it, but usually root mean squared error is used. Any questions? Yeah. So that's going to be the question is, do you usually normalize your data? So what surprised me is every time I've learned this, nobody had ever mentioned that to me, normalizing data. So since we're using distance here, basically when we get into using many predictors, if one predictor is really large and the other predictor is really small, the model is going to be biased by, and it'll show that the bigger range is more important, and that's a problem. So she asked about normalizing your data. One thing that will make it more accurate in a lot of cases is making those continuous variables, putting them all on the same scale. So either from 0 to 1 or coming back again to our z-scores that we talked about, you can change it into a z-score. Because if they're all within the same bounds, then they aren't going to bias the bigger values. That'll cover a lot more when we get into the AI side of things. It just blew me away that no one had ever mentioned that until I got into the machine learning space. So that's something, if you're going to actually use this model, look into that. If you use it before we get to that, but that is a problem. Anytime you use distance, that's important. So yes, the answer to that is yes. Any other questions? Okay. So this is the question that almost every time I go over anything like this, what is a good root mean squared error? There isn't a good answer for that. So there never is, because the units are your domain, what you're looking at is going to matter. So heart disease mortality is a pretty high number. You saw that it was in the hundreds, somewhere in the range, whereas a percent would be between 1 and 100. Just by default, if you were looking at heart disease mortality, it's going to be bigger than a percentage. It's just the way it is, the way we're looking at those units. So the units are going to matter here. So what you use this more for is when you're comparing multiple linear regression models, it's going to give you more information. So we will then go over that a little more later, looking at multiple models. Okay. So this is a really big deal. So we're going to go over R squared, just like the standard R squared first. We'll get to the adjusted one in a minute. So R squared is really important, and you'll hear it very, very often. So it's the proportion of variation in your response variable that is explained by your model. So if you are seeing an R squared of 70, that means that about 70 or 0.7 you would see. That means, and it goes from 0 to 1. So if you see 0.7, that would mean 70% of the variation in our response, so heart disease mortality, is explained by our predictor variables. So our entire model. That evaluates the model as a whole. The higher that is, the better it is. And again, there's no easy cutoff here. It's going to depend on looking for tissues, but I don't see any. It's going to depend on whatever units we have as well. If you're in public health, R squared just because, or policy, it's going to probably look pretty small because there are many variables going on. If it's something that you're looking at that has, I would say, for instance, if you're looking at our agriculture and genetics are a very strong predictor of a lot of things in agriculture. So when you looked at a correlation of our predicted versus our actual values, it was usually around 0.7. So that's going to be higher in a domain like agriculture, where genetics really is a huge determiner of how it's going to do. You have a question?
So what do you mean by explained by the model?
Yeah, explained by the model. So that variation, so you can think of it kind of in the terms of our equation. So 70% would mean that one predictor variable is going to explain the variation or the change in that response variable. The other 30% would mean that there are extra things that we are not in our model or additional things that explain the rest of that variation. So we're missing things in this case. So you can think of it as basically what we're getting, the variation that we're explaining, and that other percentage is, okay, you need to go out, for instance, and find more predictors that explain more of that error. I'm going to show this real quick because this might help. So intuitively, so in this case, we're looking at heart disease mortality and education. Clearly, education is only going to explain a small amount of heart disease mortality because there's so many other factors going on that would influence that. So you see exactly what I just said. Our R squared value is really small here. It's only explaining 5% of the variation in heart disease mortality. So our R squared value is small in this case. So we're not explaining much of heart disease mortality with education. So we'd have to go out, find more predictor variables that helped with that. So does that answer your question? Yeah. Yeah. So, and I'm gonna, So if you are thinking of it like mathematically, the third bullet is that would answer the question more in a mathematical sense. So this would be the square. So we're using square of the coefficient, the correlation coefficient. Sorry, the correlation coefficient between our predicted and our actual values. So we find we get our predicted, our actual values. We find the correlation between those and square it, and that's R squared. Okay. Any other questions?
Yeah.
Go ahead.
So when you put in the model, why did they call it multiple R squared?
So there are two. In this case, it's just going to be so that would be multiple variables. That question was, why does it say multiple R squared? That actually isn't applicable here because we only have one predictor variable. But when we go into models with more than one prediction, it's showing that it's multiple predictors. The adjusted R squared is something a little different. We're going to get to that because it's not applicable here either because we only have one predictor. Adjusted R squared is actually what we want to use for all our cases, but I can't explain it until we get to multiple regression. Okay. So now this is not an easy thing to explain. So try to picture. can go back and look at the details. So our F statistic at a very high level is our mean squares of our model. So we've seen this already. Our predicted minus our actual squared over our degrees of freedom, which is calculated with this. So basically what our model explains. So this is mean squared of model. So the sum of squares of our model is what we're looking at here. So the variation explained by our model over the mean squared error. So we, in this case, this is comparing it to the mean. So how much model does our model add, information does it add versus the mean? And then our denominator is going to be the error. So how much are we missing? And how much are we missing between our predicted and our actual values here? So think of it as a proportion, the variation explained by our model over the error in our model. So that's the F statistic, and that's how we see if our model as a whole is statistically significant. So, but if you can't understand this, because it's a lot of information, think of it as the variation explained by the model over the error. So obviously, you would want the model to explain more than the error. And if there's more error than the model explains, it's not valuable, and the p-value will be really high in that case. If we have a very high value here and a low value here, it's going to return return a p-value that is very low. So it will be statistically significant. Hold on one second. So to expound upon that, just 1 second. I'll come back to your question in just a minute. So we're assuming before we we calculate our F statistic is that all of the coefficients are equal to 0. In this case, it means there's no relationship. All of our coefficients are 0. The alternative hypothesis, and this is what our F statistic gives us, is at least one of our coefficients is not equal to 0. So it is statistically significant that it's different from 0. So that's the question it answers. And that's going to spit out a value. The bigger the better, because we want our model to explain more than our error. And then you go into something that, and I'm going to, it should have kept a link there. I guess it's not clickable, sadly. We go and edit hyperlink. So I apologize for that not working. So real quick, I asked somebody to put up here. So it's going to out a number. You're going to find that number in here. Look at our degrees of freedom, and then it's going to tell us what our p-value would be. So this is our cutoff, basically. But you'll have to go in through there and find it, but R is going to spit that out anyway. But if you want to go back and look at that table, it might help with how intuitive it is. So this is more relevant when there's more than one predictor. It's not really going to tell us a whole lot while we only have one predictor, because it is equivalent to a t-test when you only have one predictor. It's the same thing. So your question.
So in the previous slide,
Mm-hmm.
For the degrees DFE, you say n minus number of predictors. So what is n?
The question is for the DFE, what does n mean? N will always be our number of observations. Every time you ever see n in statistics, it means the number of observations in our data set. So I think it's around 3,100, whatever the counties is in our.
So essentially, in this case, it would be 3,100 minus.
Yeah.
Just removing that one.
Yes,
thing.
that
So
one
DFE
value.
Would be 1.
Yes. So the question was, in this case, would it be? It's around 3,100 minus the number of predictors. We have one predictor, so that it would be, in that case, with that example, it would be 3,099 in that case. And as I said, degrees of freedom is different for everything you look at, but it's always somehow related to sample size in some way. Like the parameters in our model and sample size, it will always be based on that in some way. So you just have to look that up, but it's always going to tell something about our sample size. And bigger is better in this case when we look at the F statistic. I'm going to go in real quick and show this example. So the F statistic is, by the way, residual standard error is the same thing as root mean squared error. What we just covered, they just call it something different in R. So if you see this, that means root mean squared error. And nobody calls it this, so I don't know why they do that. Everyone calls it root mean squared error, just makes it confusing. So our F statistic here, okay, so the actual number of observations in this case, is 3135 is going to be what it actually is in practice. I was rounding because I couldn't remember the exact number. So this is the number of observations. It's going to subtract 1. So that's telling us what our degrees of freedom is. And this is our F statistic that comes out of our model. So it is enough that our p-value is high. It's below that value. And it's just a cutoff. And that's something you have to look up because no one ever goes in and calculates the p-value from an F statistic. It's just there is a distribution, and kind of when you see here, this is our F distribution, and each one of these values has a number of p-value associated with it at a really high level. So that's what we're seeing with the F statistic. So are there any questions about that? That gives us our p-value here. Associates with our p-value. We talked about that. All right, so which one do we use? R squared, root mean squared error, F statistic. They all have pros and cons, and we can never just look at one alone. You need to look at everything as a whole. That's, and if, say, all of them are either high or statistically significant, then you're probably good to go. You're looking at a real relationship there. If, say, our p-value is 0.1 and 2 of the other parameters are really low, then okay, then we don't have a model that gives us enough information. So, and what's really frustrating about statistics, there's usually not cutoffs where one thing is, except for with p-value, that show whether it's important or not. It's just something where as you look at these things more and more and more, you start to get an idea of what's good and not. And then if you were actually using this as a prediction model, you would actually look at the predictions and see how accurate they were. And if they weren't accurate, it's not useful to you. So that we'll get to later. But so if all three agree, you're good to go. You're seeing something that's real, more than likely. Any questions? Yes.
I was trying to get my vocabulary straight. So the validation method, so that's the same thing as validating a model?
The question was, is evaluation and validating a model are the same? No. So validation is actually, we would put in a validation data set, and actually I'm going to table that because it's looking at the accuracy of our predictions. So the accuracy of the actual predicted values is validation. We're evaluating it by, say, looking at these values. Is this coefficient statistically significant? We're looking at our model parameters, basically. So all of this stuff is helping us evaluate the model. Validation we'll get to in one of the next classes very soon. But
so is this model parameters always the same thing as a performance metric?
Can you say?
Is model parameter, is that the same thing as performance metric?
The question was model parameters, is it the same thing as a performance metric? This is our performance metric. Root mean squared error is how that is considered a performance metric. So that's going to quantify how much error you have, is what you think of a performance metric as usually. So that's what, and there are several of them. Another one is mean absolute percentage error, which means something exactly what it's the mean absolute percent difference between our predicted and our actuals. So that's going to look at our actuals and our predicted every time as a performance metric. I guess our model evaluation is looking at everything. So R squared, a root mean squared error, our F statistic, our coefficients, and how they're statistically significant. It's looking at the model as a whole, basically this output. everything in here you would use to value where or not. Good question. So another thing that's very frustrating about statistics, this is a great example. Everyone calls it root mean squared error, and someone might come up to you in a conversation and talk about residual standard error. And if you didn't know they were the same thing, you might be arguing with them over what it means, and it's actually the exact same thing. So a lot of times people call things like 5 different names in statistics, and it's really frustrating because you can think you're disagreeing about something, but you're actually talking about the exact same thing. So it comes with experience. It gets better. And Google. Okay. Now I'm going to get into multiple linear regression. I know we covered a lot of that last week, but I think this is a hard thing. It's hard to understand. I wanted to go over it pretty in detail both times. This, luckily, is very similar. So this is the same concept as simple linear regression, except we have more than one predictor value. So that's what it's going to mean in this case. So we have a response variable just like we did before, but we have multiple predictors. So you can think of this as looking at the effect of multiple variables on that response variable at one time. So say we're looking, and I'm going to come in and show an example. Pull this down. So the first model we're going to look at, that's multiple regression. We're going to be looking at heart disease mortality again. And we're going to look at the percentage of high school graduation or higher and the percent married in this case. So we're looking at 2 factors and how they are associated with this mortality rate. So that is an example of multiple regression, and I'm going to run it soon. So that's what we can think of as multiple. So you would have 2 or more of these predictors in this case. It's going to do a similar thing. But you can think of it, what this means in practice. So when we have a coefficient for this percent of high school graduation variable, it will give us the coefficient. And what that means is the effect of the education while holding the percent married constant. So the coefficient is looking at basically the independent or the effect of that variable alone when controlling or accounting for everything else in the model, is how you can think of it. So you've heard the thing controlling for X variable. That's what that means in practice. We're pretending percent married is constant, and then we're finding that relationship between the education and the mortality rate. So that's one way of thinking of it. And here, exactly what I just said. Interpret the coefficient as the average effect on Y of a 1 unit increase in the predictor while holding other predictors constant. So this is a mathematical. You would explain this to somebody, and you can see why this is a weight here. So if we're going up, in this case, let's go here. So if the percent high school graduation or higher, it increases 1%, because we're looking at percentage points here. The coefficient is going to mean, so it increases by one unit or 1%. The coefficient tells us the average effect, or how much it will increase when we increase that value by 1 unit or 1%. Come in here, I'm going to show just real quick. We saw this one earlier. I am going to output our summary. So MLR, multiple linear regression 2. So we're going to go over this and more. But what that means in practice, as the percent of high school graduation goes up by 1%, then our response variable, heart disease mortality, goes up by 1.8%, or 1.8 units, sorry. So that heart disease mortality goes up by 1.8, basically a 1.8, as the percent of high school graduation or higher goes up by 1%. So I was looking for that earlier in the class, and because I wanted to explain that. That makes it a little more intuitive. That's why in data science, the linear regression is so heavily used, because that, when you don't get any of the modeling stuff, that makes sense to it quantifies, basically. You can think of it as weight. You actually can, and you can explain what that means in practice to someone and they get it. That's why you always default to the simplest model, because it's usually the easiest one to explain, and it prevents overfitting, which that is important here. So I actually didn't put this in the slides, but this is something we're going to come back to over and over again. Say I had, in this case, in my data set, I have 17 variables. So some of them are identifying what the counties are. So I have about, I'd say, 14 response variables that predictor variables that I could potentially use in my model. Why is that a really bad idea to put 14 things in a linear regression model? The reason that's a really bad idea, so when we're looking at our predicted and our actual values, usually in practice, we're actually using this to calculate prediction. So when we use too many parameters or control variables, it is going to really, your predictions will not generalize to new data, or it will be so specifically tailored to your training data, or the model that you're training, the data you're training the model on, that when you drop in new data, it's going to be ineffective. The predictions are not going to be accurate. That, if you don't totally understand that, we'll come back to that again and again and in more detail. Okay. Any questions about that before we move on? Feel free to put questions on Slack, because I'm totally aware. That's why I make this like a cap at 2 hours. I'm going to stop at 12:30. This is a lot to take in, and then you kind of have to go back. One thing that I do recommend, that I've done, and pretty much anytime I learn something new, in the statistics sense, programming is a little different. I do something like you're doing today, get a high-level overview from someone. Then I find either videos online. Khan Academy, I have not used it myself, but people say that's a great place to go every time. I don't do well with verbally getting information, so I tend to not go for the videos because it doesn't sink in. So what I've usually done is get two or three textbooks, read the most general one, and okay, that sort of makes sense to me. Then I would go to a harder textbook. Okay, then I added a little more information. I understand it a little better, and then I would go on to maybe the third one. Okay, now I get the details. If what one person misses, usually someone else. Then after reading multiple descriptions of it, you'll understand it a lot better. So I do recommend something like that. It doesn't have to be a book. It can be videos. It can be Coursera. It can be anything. And that way you're getting multiple perspectives on this. And then usually the book will cover things that I don't cover, or I don't have time to cover, or I don't explain as well as other concepts. So I recommend doing that. So I told you that the R-squared, we don't usually use that in practice. We usually use the adjusted R-squared. This comes back to overfitting, what I just explained to you. So the more predictors we add, the more tailored our predictors are going to be to our training data. So we don't want to have too many. The adjusted R-squared, when we look at R-squared, it's always going to increase by different degrees, but it's always going to increase as we add more predictors. It's the correlation always going to increase. It's the way it is, the predicted versus the actuals. So in that case, the R-squared would keep getting better no matter how many predictors we added, even if those predictors weren't really adding any value. So it's still going to look like it's getting better. The adjusted R-squared deals with that. So it basically penalizes you for having a lot of predictors. It penalizes that R-squared value, so that that we're taking into account how many predictors we have, and it helps you prevent overfitting. So if you're having 3 predictors that have literally no effect on our value, it's going to penalize you for those. Whereas if you have 3 predictors that really do explain a lot of the variation, it's actually going to look higher, a lot higher when we do penalize for, it's basically trying to take out the effect of things that are not helpful. And down here, I'm not in detail, but you think of it as penalizing for the number of predictors. So, and this, there's one more assumption that now that we're using two variables, this comes into play because it doesn't apply when you have one. So basically another thing for linear regression, and this is actually for machine learning and anything. If your predictors are highly correlated or they vary in similar degrees to one another in the same direction, so highly correlated with one another, then it biases our model. They have to be independent of one another. You'll remember that I went over that. So you have to, one of the assumptions is that your coefficients have to be independent. The interaction variable, which is at the end of my slides, is the one caveat to that. But our predictors have to be independent. If they're too correlated with one another, our model is no longer valid. Okay. So I am going to go over one more thing before, then I'm going to show a full example. So how do you assess multicollinearity? This has to do with our R squared. So the formula is very simple. 1 over 1 minus the R squared value. That's called the variance inflation factor. Most of the time it's just called VIF. So over here, there are cutoffs for this one, actually. So that's really helpful. If it's around 1 or 2, there's really no multicollinearity happening there. If it's 4, you're getting to the point, that's like a yellow. Like look into it more and see if we are actually having multicollinearity. If it's above 10, we got a problem. So that means our model is very biased. The more predictors you add, usually the higher these numbers get. And there's going to be a great example of that soon. So I'm going to go in and show examples of that. So hold questions if there's any until then. So there's one other really useful thing. So how do you pick which predictors to put in your model, other than looking at the coefficients and whether the p-values are high or not? So there's another way to look at it. So we started off, and I think this is better shown with the code. We started off with one predictor, this one. That was our first model. This is just the same as our first model. And I'll explain why I put it down here in a minute and redid it. So the next thing I want to try is percent married in the percent and that same variable we looked at before. I'm going to do that. And the first thing you want to do is look at the outliers. If you don't have this, if you ever see that, it means your window isn't enough to show the graph. It's yelling at me. So here, if you have our Cook's distance again, you have to look really, really close to that to see what the numbers are. But this is telling us what our outliers are again, if you remember. The third model I wanted to look at is percent, basically the same, but I'm adding the percent uninsured. So that's the percent that don't have health insurance in each county. So I am going to run that and also look at the outliers. So that gives us a different set of outliers. Here, this is the easiest way to show what counties are the outliers. You'll see here, this is the row number. If you want to know more about this, go to the R programming. And this is the column number. The column number 1 is county. And so one of the outliers is 68, you can see here. So if I use this code, it's going to dump out what all my outliers are. So these are all the outlier counties. And then I'm removing them here is basically what's happening. So I'm removing all of them for all of the models that I'm about to run, and I'll show why in a second. That's why we're redoing all this. So we're going to run our most simple model. We'll see our summary here. So that is the most simple model. And then we're going to run the ones, crap, did we not? MLR data, I don't know why it's doing that. Hopefully. What? We're not getting an error there. MLR data. There we go. I don't know what was going on there. So we're starting off with our most simple model here, adding percent married here, and we are going to add again the third variable here. So now I'm going to go up and show what this actually. So as I said, multicollinearity, there's no predictors that can be correlated with one another. We only have one predictor. That's why it's not applicable when we have simple linear regression. You can't calculate it. Here, we want to look to see if the percent of high school graduates and higher is correlated with the percent married. It's telling us our VIF scores are real close to 1, so we're good to go there. Now we have 3 variables now. And our VIF scores are these. So they're a bit bigger. That's what you would expect, but they're still close to 1, so we do not have a multicollinearity problem. They're not correlated enough with one another that it's biasing our model at this point. And I'll show an example that is the opposite of that very soon. So now we've run 3 models. Like, everything is still statistically significant. If you look up here, so our coefficients are significant, and these our model is significant. So which one do I use? This is the third way, the preferred way that I would use. So if you want to see the assumptions, you can go over here and check your assumptions. I already did, and they're good to go. So I'm not going to cover that again. But the ANOVA function helps with this. So this is not to be confused with AOV, the function AOV, that we actually run an ANOVA on some data. It's a different function. And make sure this is lowercase, because there is an capital A ANOVA function too. So this is the one you want, the lowercase ANOVA. What this is going to do is going to run an ANOVA, and I'm going to go back into my slides for a second. It's going to compare the models with different numbers of predictors. So basically, when you add one predictor, it's going to compare those models side by side and look at how, if they add a significant level of value. So basically, how much additional predictors reduce our residual sum of squares, so our error. How much does adding that extra predictor reduce our error value? And then it returns a p-value. So now we'll see here, running the ANOVA. So you can see up here what model 1 is and what model 2 is and what model 3 is. Well, we want to look at our F statistic here. The model 2 is actually the best. So percent uninsured didn't add enough value to make our error values go down. So it was significant, but this model is going to give you the most accurate model, which you might not expect. But since we are comparing them side by side, we know that this is the case here. So then we would pick this model. So why did I redo and take out all the same outliers for all the data sets? And make sure, there's a reason I redid everything. So you'll remember we only, for this one, got rid of 1 outlier, whereas in these 2, I think we got rid of 5. I'm going to try to run that. Error in ANOVA. Models were not all fitted to the same size data set. They have to have the same number of rows in order to run this, or it will throw an error and it won't give you an answer. So that's why I was redoing work that we had already done. All right, there's one more concept over at stopping for questions.
So you evaluated the 3 models and decided 2 is better than 3. If you look at the variables independently of linearity before you added the model, is that another way to do that?
Yes, but just in general, that's kind of like looking at the R squared and the root mean squared error. You kind of have to take multiple factors into account. This should be your default, to be honest.
Okay. Because
we really care about error. And this is a great way, if you can, because if you have different number of rows, you can't use it. So you can't use it in every context. So then you would have to try something else. But in this case, it's telling us how much value is added by that extra variable and by reducing error. So the significance does not always mean that it's valuable, actually.
Well, we just looked at that additional variable you added. Just like correlation.
So it is significant, but in this case, and I was actually surprised by this. I didn't totally. So in this case, the error value, for some reason, it's not increasing our prediction accuracy is enough to make it useful. It's not significantly, it might be better, but it's not significantly better than the other one, is what you can think of it. So here, just to go over more about multiple regression. So in this case, just to reiterate, if we're looking here, and here you can see it. So our t-value is 10 here versus negative 17 and 15. So that's how significance is actually calculated. So this value might be bigger, but and the reason it would look like this. So the uninsured might be, in general, the mean might be bigger than the percent married. So remember I said units matter?
So if you normalize it, maybe.
Yeah, if you normalized it, you would see this as lower. Yes, so that's a great example of why normalizing is also really important. So this is just going to be a higher value, but when we actually, because the t-statistic is normalized, it's smaller. So it is not adding enough value to give more value than say, it will overfit more than it adds value is a great way to say. But here, so kind of coming around, so the percent uninsured in 2014, so as we increase that percentage by 1%, we're seeing an increase in the heart disease mortality of almost 2 here. So that's what that means again, just coming around. And our adjusted R squared, you see it went up. When we only used one variable, it was basically 5%, now it's 20%. So we're doing a better job of predicting that heart disease mortality. But that's still low, just FYI. In almost no cases is 0.2 going to be a good R squared. So, all right. Are there any other questions?
Yes.
Go ahead.
I have a question. Is ANOVA appropriate really for linear regression models, or can it be used on other?
Yes. So the question is ANOVA, can it be used in other circumstances, not with linear regression models? The answer is yes. So I did a whole class on ANOVA, so I would recommend going back and looking at the ANOVA. It's very, very, very useful for experiments. That's usually how it's used to evaluate experiments that we do. Like, say you're looking at the effectiveness or in that case, seed return based on region. So we could look at and compare the different regions and how much seed return varies by those different regions. That would be a use case. But for that function is specific to linear regression though. Yeah. Any more questions?
No.
Yes, we have some time, so.
What? No, the R squared, does that cover it in another class?
No, we covered it earlier. So
I didn't even.
Find it, R squared. So that means it's the Pearson's correlation coefficient between the predicted and the actual values, and then we square that. And what that we covered last class. So those videos will be up, but it's looking at the relationship between the predicted and the actual values and whether they vary together, basically.
Oh.
So for more details, that was in the last class, and I will have the videos up pretty soon. The holidays have been just extremely busy. So, but the slides are up, by the way, already. So that would go back to an earlier class. All right. So the last thing I'm going to cover is interaction effects. This is one of the things that I struggle with explaining this a lot, actually, when I've looked at this. So I'm going to give it my best shot. And I tried to give a lot of examples here because I don't think it makes sense outside of the examples. So I remember I said that two predictors have to be independent of one another. There's actually a way to look at both of them at the same time, and that's called an interaction variable. So when you put it in the model, in that case, you would put predictor, and then you add a third predictor that is predictor 1 times predictor 2. So you multiply them together in your model. That's called an interaction variable. And you want to do that when you suspect that one variable, the effect of one variable, will depend on the effect of another variable. This, I haven't seen anything that was quite as intuitive to understand as this. And I'm going to give an example from ours as well. So interaction effects, I really recommend going and reading this because I thought it was really, really well done. So this would be an example. We're looking at anxiety level and then the effect of an anxiety drug here. So we're looking at men versus women. You'll see these two are parallel. So that means that the effectiveness of this drug does not, there is no interaction between the anxiety level and the dose and gender. So we're seeing a change in anxiety level that's similar, the rate is similar for the dose for male and female. Now the opposite of this. So here you can see for female, the bottom line, the dose is increasing, anxiety level is decreasing more here. So our slope is bigger here. Whereas in for males, as we increase the dose, the anxiety levels don't decrease quite so fast as with females. So the slope is kind of, you can think of it as the rate of change. So the change in anxiety level with different, as you change doses, is different for males versus females. And there's a lot of explanation here in more detail. I thought that that was pretty intuitive, but I'm going to give you a second example. That's, I had never teach a class. So I didn't know that this was available. So in this case, we're going to look at the percent below poverty, percent married, the percent uninsured, and the percent below the poverty level. This is our interaction variable. So we're looking at the relationship between the percent below poverty and the percent uninsured. One rule that sometimes even advanced statisticians don't know, if you put it in an interaction variable, you have to put it alone in our model. So this will also serve as showing what a multicollinearity problem is. You saw I had a lot of predictors in there. Particularly with interaction variables, since you're putting it in there twice, they tend to correlate, your predictors correlate a lot with one another. This is actually the best example I could find. So I'm just removing outliers here. That's all. You can go back and look at that. So I got rid of my outliers. We got our model. Look at our VIF scores here. They're all bad except for percent married. So our multicollinearity problem here, and this is a great example, you need to be very wary of your model results when you see something like this. But I did want to give an example of an interaction variable. You would see probably less of this as your sample size got bigger, but our sample size is relatively small, around 3,100. So it's, in this case, it's really bad. This is not good. So keep that in mind when evaluating the results I'm going to show. So we have here, and I need to actually, so the thing about R, it will change what it shows based on how far it's open. Okay, so reprint that. Here we go. So if you see that graphics error thing, just rerun your code. I don't even know what causes it, but it shows here. So our coefficients are percent below poverty, percent married alone, percent uninsured alone, and then we have the interaction between percent below the poverty level and the percent uninsured. So this is significant, but it doesn't really make sense. So, and it's hard to see and understand this unless you do something like this. And I didn't know that this was a thing until I did this class. So it's really neat. This actually helps you visualize it, hopefully. Yeah, there we go. So I'm actually going to make this as big as I can. Loading. Okay, just so you can see this in more detail. So this is what it means, that particular coefficient in practice. And I recommend doing something like this because I can't even tell you. It's hard to understand a literal interpretation of that coefficient. So here it's showing a percent uninsured that's really, really low, 1.6. Then it's showing a percent uninsured that's really, really high, 0.45. The percent below the poverty line is on the bottom. And then in this case, we're looking at life expectancy. I wanted to give another example. So in this case, we're seeing that when percent uninsured is really low, the percent below the poverty level has a gigantic impact on our life expectancy. Whereas if the percent uninsured is really high, the percent of the poverty is not having a big effect. Why you see that? They're probably very highly correlated with one another in practice. The people who have high uninsured rates are probably also going to be high on the poverty level scale, which is also why we're seeing a huge multicollinearity problem. So that shows you in practice what we're seeing there. So if they're already high in poverty, they probably don't have insurance. Whereas if we are low, we have a low percentage of uninsured, that really makes a big difference, the poverty level associated with it. So basically the insurance isn't adding more, or it doesn't add a whole lot more information than poverty level would show. Does that make sense to everyone, that particular graph? And then intuitively, given my public health background, that some of them I put them on here and I tried a bunch of different variables and some of them were very hard to like think of a reason why, basically. But that one was pretty intuitive. But again, that's why we're seeing this. So this is a huge, so they're very highly correlated with everything else in the model. So, all right. So that's all this I'm covering today. We have a couple minutes for questions to go over, and I can stay after class. We have the room till 1, so feel free to kind of hang out or ask questions after if you want. I just didn't want to give any more information than this, but I can stop for questions now. I'm going into the chat in case there's something in the chat. All right.
So you mentioned textbooks. Are there any textbooks that you recommend?
I did put one in the class materials. So it's a very basic one. I believe I put it. Hopefully it's still on here when I've done this. So I'm not sure if I did. So statistics. If somebody can help me out. I do think somebody put it on the Slack channel though. I can't remember the name of it, but I do remember. So the one that I put in for the actual class is pretty basic. So it's going to give a really high level understanding of it. So hopefully when I open the Slack, it'll go to this and then we can see. Someone posted it a while back. So it is a really like high level understanding of it. I hate how slow the internet is here. Obviously we have like a lot of conversation on the class Slack channel. This is, you can talk to everybody, and I would actually no, that's with a student. There we go. So we go back up. These are where people can ask questions. This one, data analysis with R. Thankfully somebody put that up. So this might look different. There's different versions. They're pretty similar to one another. It doesn't really matter. But We'll see Tony Fischetti, data analysis with R. This is very high level. There's very little detail in here. Discovering statistics with R, if you want to get more detail and more of the math, I recommend that one. I'll leave this up for a second, then I'll show discovering statistics with R. It's actually what I used in my graduate school class. It was the SPSS version, but they used that textbook. It's a lot more technical than this one. So I'm going to go in and so this is what this one looks like. I believe Andy Field is a pretty highly regarded statistician. So discovering statistics with R, I can't seem to zoom in on that. So I know Amazon lets us do it. So there, I think both of these have an ebook version and a regular version if you want to have the paper copy. So putting this up. This is more technical. This would be your number 2 if you wanted to go in. I would recommend reading this one second. I'll go away. So, yeah, it's just the Wi-Fi here is not particularly good. So there you go. That's number 2 that I would recommend. And Khan Academy, if you're good with videos, is a really good one to go to. KHAN, Khan Academy. I don't personally use it because I don't like videos a lot. And actually, another thing that I would recommend, so I believe that there is another video form if you want 2 videos. AWS. AWS certification training. If you go in training and certification, they have a lot of math here. They have like machine learning, they have linear regression. You'd have to find it, but it will have a like basic statistics course, and I think it's like 8 hours long. So it's a pretty good. I haven't looked at it myself, but I did get my cloud practitioner certification recently, and I thought that the videos were quite good. So I do recommend those as well. If you go to this, the dashboard, the learning library, it's going to be in here. And if you're interested in cloud is running analyses on the internet. It's going to be up here too. You'd want to go to the free digital training, and it'll have it on there, and it has a lot of different stuff. So it would probably, and then you're going to want to do English because there's a lot of second languages, which is good. If you speak something other than English, it'll probably be on here. So that's good as well. So I'm done with all the content. Feel free to ask questions, but if you want to get off, that's good too. So I'll stay up here. If you have any questions to ask, or if you want to do it now, it's good. In front of the class, it's good too. Mm-hmm.
So for earlier for the whole progression, you were adding like your cross product, I guess, right?
Yeah, it's so the multiplication of them basically. So it's called an interaction.
Interaction items. So I guess I usually use Jump. There's like a tool that kind of does like full factorial, or does like a stepwise thing where you can do everything and then throw out the ones that suck. I guess that
yeah, well, that's what I just showed. The stepwise is when I did the ANOVA. That's what it's going to be. It's going to be the same thing actually. So not that one, this one. So this was with one, and then I used the same predictor, added another one here, used those same predictors and added another one there. That's the right way to do that. You can't use this, or you're not supposed to use this. So we have one, and then we have 10. It's going to add most value if you do the stepwise. It's like just like you said.
But I think in that case, you specified the variables in each
yes.
Is there something that where it just takes like a blanket all the variables?
Question is if there's something that takes blanket all the variables, that would be bad math. So I wouldn't recommend doing that because if you have a lot in your data set, it's automatically going to be overfitted. Right. So that's bad math practice, I would call it. So
So the question he's asking is, the particular jump routine called stepwise, where it adds all the terms, or removing them or
So you
adding
don't
them
have the
based
base
on p value.
So what they're doing there more than likely is they're like doing one at a time as well.
Right.
But if you have 14, say, that will not be a good indicator. Just because you can't have, that's the one, machine learning is a lot better because you can throw the kitchen sink at it.
Okay.
You can throw 20 variables or 30 variables or even more than that, depending on the model, and it won't overfit. If you have, it depends on your sample size, but I would be very wary of having more than 5 or 6 at all. And for something with 3100 basically, you're going to see like this. I have 5 here, and it's obviously extremely problematic. And I couldn't find a single example that looked better than this. It was all bad because I'm overfitting. I have too many predictors for my response variable, and this shows exactly what's wrong with that. Because it's not this model is not, it's biased. It's not useful because they're too highly correlated with one another. I wouldn't use this model in practice, but I couldn't find an example that looked good. Even when I used 2 predictor variables and found an interaction between 2 of them, it didn't. They were all bad. So, and that's because we have too many predictors. So that's the other way. So not to disagree with jump, but I would, and then you can do it stepwise as well. So you could try another variable first. So instead of starting with the height education, move to % uninsured, and then say add education onto that, and you can see in addition to that % uninsured how much value is that new variable adding. So the order matters here as well. So I usually try a whole bunch of things. And then when you try it in multiple different ways, if it's not useful for 5 different models, it's not useful anywhere. So that's, I think, a better way of doing what you're talking about. Try different orders and try it in combination with a lot of different variables. That is going to come more in that you do, that's feature selection, which is also a big thing in machine learning, and you do it the same way. Although there's a better feature importance metric that you can get out, and there's a bunch of different ways to do that, but that's a little down the road. But what you're doing there is feature selection. There's other ways to do it other than stepwise that are actually better. I've always done it with stepwise, but apparently that it's not. Some of the people I work with think that that's a bad way to do it too. So I don't know what their alternative is. But any other questions? Chat. All right, I'll be staying up here for a little longer. We got it till 1, so you no need to rush out. I will post the videos as soon as I can. I apologize. Stop recording.